In 128 AD, Roman engineers poured a concrete dome 142 feet across. No steel, no rebar, no reinforcement of any kind. Nearly 1,900 years later, it is still standing, still the largest UN-reinforced concrete dome on Earth. In 2018, a bridge in Genoa, Italy collapsed. It was 51 years old. 43 people died. In 2021, a condominium in Surfside, Florida, collapsed in the middle of the night. It was 40 years old. 98 people died. The steel inside the concrete had corroded so badly that the building destroyed itself from within. The Romans built structures that heal their own cracks. We build structures that eat themselves alive. The difference is not technology. It is a recipe. One that worked for 6 centuries, then vanished for 13 more. When scientists finally found it, what they discovered had been dismissed as a defect, a mixing error, a mistake. It was the secret to concrete that lives forever. And a $410 billion industry has no intention of using it. The story begins near the Bay of Naples around 300 BCE. The town of Pozzuoli sits on top of Campi Flegrei, a volcanic caldera 13 kilometers wide. Over 24 craters lie beneath the surface. The ground breathes. The soil smells of sulfur. The ash that blankets the hillsides holds a chemical secret no civilization has ever encountered. When this ash is mixed with burned limestone and seawater, it does not just harden. It becomes stone. It sets underwater. Over time, it gets stronger. They call it pulvis puteolenus, the powder of Pozzuoli. We still call any volcanic ash that reacts this way pozzolanic. The word comes from this town. The recipe is simple: quicklime, volcanic ash, seawater, volcanic rock, mixed hot, packed by hand into wooden forms. No steel, no rebar. Their arches and domes keep the concrete in compression. Gravity does the work. Around 30 BCE, the architect Vitruvius writes the formula down: 1 part lime to 3 parts ash for land, 1 part lime to 2 parts ash for underwater. Rome ships thousands of tons of Pozzuoli ash across the Mediterranean as ballast in trading vessels, and then they build things that refuse to die. The Pantheon was poured around 125 AD under Emperor Hadrian. It has a dome 142 feet across, a perfect sphere, heavy travertine at the base, light pumice at the crown, 4,535 tons of unreinforced concrete. It held the record for the largest dome on Earth for 1,300 years. The Aqua Virgo Aqueduct, built in 19 BCE by Marcus Agrippa, is still functioning. It still carries water to the Trevi Fountain in Rome. Over 2,000 years of continuous operation. Roman harbor piers at Caesarea and Portus Cosanus have been submerged in salt water for over 2,100 years. They are still intact. In 79 CE, the Roman historian Pliny the Elder writes that concrete submerged in the sea becomes a single stone mass, impregnable to the waves, and every day stronger. Months later, he sails toward Vesuvius to observe its eruption. He never returns. The volcano that killed him is the same volcano whose ash built everything he admired. For 6 centuries, this concrete builds an empire. Temples, tombs, markets, harbors, aqueducts, walls that survive earthquakes, floods, and invasions. Then Rome falls, 476 CE. The Western Empire collapses. The supply chains that moved volcanic ash across the Mediterranean break apart. The craft guilds dissolve. The knowledge passed from master to apprentice for generations goes silent. Vitruvius's book survives, but words on a page cannot replace hands that knew the work. For 1,300 years, no one on Earth could make what the Romans made. Marie Jackson, a geologist at the University of Utah, put it plainly. The recipe was completely lost. In 1824, an English bricklayer named Joseph Aspdin patents a new material, Portland cement. It will become the foundation of the modern world. But it is not the same material, not even close. Portland cement is made by heating limestone and clay to 1,450 degrees Celsius and grinding the result into powder. Mix it with water, sand, and gravel. It hardens. It is strong enough to hold up skyscrapers, dams, and highway overpasses. But it carries a fatal flaw built into its design. Modern concrete needs steel, rebar, mesh, reinforcement threaded through every slab and beam to give it tensile strength. And steel, when it meets water, corrodes. Water seeps through pores and microcracks. It reaches the rebar. Rust forms. Rust expands to 2 to 6 times the volume of the original steel. The expansion cracks the concrete from within. The cracks let in more water. More water makes more rust. More rust makes wider cracks. Modern concrete does not just fail. It accelerates its own failure. Every crack makes the next one worse. It is a material at war with itself. Typical lifespan, 50 to 100 years. Some marine structures begin corroding within decades. Roman concrete had no steel, nothing inside to corrode. Water could not destroy it because there was nothing to attack. When cracks formed, the material did not get weaker. It healed. This difference should concern us. It does not, because the material that fails is the material that sells. The global cement market generates $410 billion a year. 4 billion tons of cement are produced annually. If the cement industry were a country, it would be the third largest carbon emitter on Earth. That is 8% of all global carbon dioxide emissions. 2.8 billion tons per year. More than aviation. More than shipping. In the United States, 43% of cement demand goes to roads and bridges. The same roads and bridges crumble every 50 years and must be rebuilt. Over 42,000 American bridges are rated structurally deficient. 220,000 need repair or replacement. Americans cross structurally deficient bridges 200 million times every single day. The American Society of Civil Engineers gave the nation's infrastructure a C in 2025. The investment gap is $3.7 trillion over the next decade. The math is not complicated. Concrete that lasts 50 years creates a market that renews every 50 years. Concrete that lasts 2,000 years does not. A material that heals itself is a material that cannot be sold twice. For decades, scientists who studied Roman concrete noticed something strange. Scattered throughout the ancient material were small white chunks, bright, calcium-rich mineral deposits called lime clasts, millimeters wide, visible to the naked eye. Every researcher who examined them reached the same conclusion: sloppy mixing. The Romans had failed to fully blend their lime into the mix. These were defects, mistakes, evidence that even Roman engineering was imperfect. No one questioned this assumption for decades. In 2023, a professor of civil and environmental engineering at MIT named Admir Massic asked a question that no one had asked before. If the Romans spent centuries optimizing this recipe, why would they leave such an obvious flaw? His team analyzed concrete samples from Privernum, an ancient site near Rome. They published their findings in Science Advances on January 6, 2023. The lime clasts are not defects. They are the self-healing mechanism. When a crack forms, water enters. The water dissolves calcium from the lime clasts. A calcium-rich solution flows into the crack. The calcium recrystallizes as calcite, sealing the crack shut automatically. No human intervention, no repair crew, no maintenance. Massic's team built the proof. They manufactured concrete using the Roman method, cracked the samples deliberately, and ran water through them for 30 days. The water flow stopped completely. The cracks sealed themselves. Control samples made without lime clasts never healed. Roman concrete can seal cracks up to 0.6 millimeters wide. That is double what any modern self-healing concrete approach has achieved. The key was something researchers call hot mixing. The Romans did not pre-slake their lime into a smooth paste the way modern builders do. They mixed raw quicklime directly into the volcanic ash at extreme temperatures. Localized hotspots exceeded 200 degrees Celsius. This violent reaction is what creates the reactive lime clasts, the calcium reservoirs that sit dormant in the concrete for centuries, waiting for a crack to activate them. What every scientist had dismissed as a mistake was the most sophisticated self-repair system in the history of construction. But Massic's discovery was only half the story. 6 years earlier, in 2017, Marie Jackson published a study in the journal American Mineralogist that revealed something equally extraordinary. When seawater filters through Roman marine concrete over centuries, it dissolves components of the volcanic ash. This creates highly alkaline fluids, and from those fluids, two rare minerals grow: a luminous tobermorite, plate-shaped crystals that reinforce the concrete matrix, and phillipsite, interlocking mineral fibers that bind everything tighter. These minerals do not just preserve the concrete, they make it stronger. Every century, every tide, every wave. Jackson said it best: no one has produced tobermorite at 20 degrees Celsius. Oh, except the Romans. Modern Portland cement is designed to be chemically inert. Any reaction with the environment is damage. Roman concrete is the opposite. It is designed to react. Every interaction with water and seawater makes it harder, denser, more resistant. The concrete, Jackson said, was so well designed that it sustains itself. Two mechanisms: lime clasts that seal cracks within weeks, mineral growth that strengthens the material over centuries, a concrete that does not decay. It evolves. And then came the final proof. In December 2025, Massic's team published again, this time in Nature Communications. They had excavated an active construction site in Pompeii, Regio 9, a building frozen mid-construction by the eruption of Vesuvius in 79 CE. In the rubble, they found piles of dry material, quicklime pre-mixed with volcanic ash, exactly the hot mixing process Massic had theorized 2 years earlier. The Roman workers were caught in the act. The volcano that killed Pliny preserved the proof. 2,000 years of evidence, hiding in plain sight, dismissed as a mistake by every scientist who looked at it, until one of them asked the right question. Massic did not just publish a paper, he started a company, DMAT, headquartered in Udine, Italy. Their product uses the Roman hot mixing principle to create concrete that heals its own cracks and cuts carbon emissions by up to 60%. In October 2025, the company raised $4.5 million to scale production. It is already certified in Europe and already deployed on highway infrastructure in Italy and Switzerland. The United States is next. Meanwhile, Marie Jackson received a $1.4 million grant from ARPA-E, the U.S. Department of Energy's Advanced Research Agency. Her goal is to create synthetic volcanic materials from recycled glass, engineered as replacements for the ash the Romans pulled from the hills above Pozzuoli. Her target is an 85% reduction in energy emissions and 4 times the lifespan of current marine concrete. And in the Netherlands, a marine biologist named Henk Jonkers took the idea further. He embedded bacterial spores directly into concrete. When cracks form and water enters, the bacteria wake up, consume calcium lactate, and produce limestone that fills the gap from within. Living concrete. His company, Basilisk, has deployed it in over 30 projects across Europe. The self-healing concrete market is projected to grow from $220 million to over $1 billion by 2033. The science exists. The companies exist. The products are being poured into roads right now. But the industry they are trying to change produces 4 billion tons of cement a year. It generates $410 billion in annual revenue. It accounts for 8% of all carbon dioxide released into the atmosphere. And 43% of its demand comes from rebuilding the same roads and bridges that keep failing. The pattern is not new. Black locust wood lasts 100 years without treatment. Pressure-treated pine lasts 15 years. Pine is sold at every hardware store. Black locust is unknown. Hempcrete builds fireproof walls and pulls carbon from the air. Hemp was banned in America for 81 years. Roman concrete heals its own cracks and gets stronger in seawater. Portland cement cracks, corrodes, and crumbles. It generates the same $410 billion a year in replacement revenue. The question has never been whether we can build things that last. The Romans proved it. The Maya proved it with tree bark mixed into lime plaster that survived 1,000 years of jungle. The Chinese proved it with sticky rice mortar that holds the Great Wall together. The question is whether the system that profits from failure will let us. 42,000 structurally deficient bridges, 98 dead in Surfside, 43 dead in Genoa, 2.8 billion tons of carbon dioxide every year. The recipe was lost for 1,300 years. We found it. The only question left is whether we use it. The Pantheon Dome has stood for nearly 1,900 years. No steel, no rebar, no maintenance, no cracks. Somewhere beneath the streets of Pompeii, a pile of quicklime and volcanic ash sits exactly where a Roman worker left it on the morning Vesuvius erupted. He was building something meant to last forever. We still can. If this vault opens something for you, subscribe and hit the bell. Every like and every share preserves what they tried to bury. The next vault opens soon.